Hello BC Part 1, how are you? So in this screencast, I am going to walk you through two derivations in your textbook. And the reason for that is twofold. What we're going to start doing in a very gradual way is we're going to start reading a math textbook, okay? And what I may do is things like this, where I incorporate that into homework, because I do think there's something that's incredibly valuable in terms of following a proof, all right? And this proof is just lifted right from your textbook. What I want to do is walk you through it. Now, I will say, Arjun, there are some students who may choose just to kind of gloss right over this proof because you never have to duplicate a proof on your own, okay? However, I will say that walking through a proof and being able to read mathematically has a direct positive correlation with your performance on calculus tests. The two are one and the same. Being able to follow someone's work, especially a proof, okay, being able to read a proof requires skill, and it becomes easier the better you get at math in general, calculus in particular. Okay, so this proof here is going through what's called the quotient rule. Like, what happens if you have, if y equals, say, 3x squared plus 2x plus 11 divided by x squared minus 16, right? How do you find dy dx, right? This, if you had this function, you were asked to find dy dx, you would have some difficulty. Now, if I didn't have, like, if there was no negative 16 here, you could do it, because you could take each term divided by x squared, then just use the power rule term by term. But if you have x squared minus 16, you can't do that. So what do? What is the derivative of a quotient? So this right here is saying, what is the derivative with respect to x of f of x over g of x? Now you're going to follow me through. The first thing that's done from here to here is look what they use. They use the definition of the derivative. Okay? This is, if you look at this, this is just f of x plus h minus f of x all over h, and g of x plus h minus g of x all over h. Okay, so this is just the definition of the derivative. Okay, and this is kind of neat too. Look what they did here. What happened is you look at this. It's called a complex fraction when you have a fraction within a fraction. And what was done here was the numerator was combined, finding a common denominator. And by the way, that common denominator would have been g of x times g of x plus h. And then we multiply by the reciprocal of 1 over h, so we're here. Okay? And this is a slick trick. I highlighted it. For this derivative rule to be worked out, for this proof to work out, you have to do something really slick and savvy, and it's this: adding and subtracting some quantity within the numerator. And if you look, it's right here. If you subtract and add the same entity to something, that's a perfectly valid thing to do, right? That doesn't change the value of the numerator. It doesn't change the value of the limiting argument, okay? And then look at the next step from here to here. I kind of gave some little anecdotes. What happened in the next step was, if you look over here, the first two terms were grouped, okay? And the second two terms were grouped, right? And if you look at the first two terms here, f of x plus h times g of x minus f of x times g of x, the constant factor there is g of x, factored out, and you're left with, in the parenthesis, f of x plus h minus f of x, okay? And the over h, that comes from, I'll show you in a second, so there's a couple things going on. That comes from, if you look over here, see this h in the denominator? Okay, they reverted back to a complex fraction up here just to make things work out really nicely. So this denominator becomes this denominator because the h, popped up to the numerator. Okay, this second grouping was factored by grouping. All right, and then I want you to look right here, and this is where you can kind of assess, how strong your somewhat semi-regular review of calculus is. If you look right here, now this is just the limit of a difference equals a difference of limits, and a limit of a product equals a product of limits. So all this was done here was, I know you want to say distributed the limit, that's not what's going on, but the limit of the entirety was just re-expressed as a components, like limit components, right? The limit was applied to each component piece of the argument, okay? And the question I have for you in red here is, in this green, do you see f prime of x and g prime of x? I hope you do, because f prime of x is right here. Look what I'm taking. And g prime of x is right here by definition of the derivative, which then brings us to right here. I'm going to erase this green, okay? Now we're at this step, right? The limit as h approaches 0 of this, that is just, they're calling it d by dx of f of x, which is just f prime of x, okay? This is g prime of x, or d by dx of g prime of x, g of x, all right? And then, this is actually very interesting. As h approaches 0, what will g of x approach? Well, first of all, everyone, g of x doesn't have any h in it. So if h is approaching 0, g of x just remains, come with me, g of x, right? F of x, as h approaches 0, there's no h in f of x. So f of x just becomes, look at this, right here, just becomes f of x. And what you have here is the final at the end of the day. Now, there is a much more user-friendly way of writing this. It's writing it this way. The derivative with respect to x of a quotient just equals f prime of x times g of x, the derivative of the numerator divided by the denominator untouched, minus the numerator untouched times the derivative of the denominator, all divided by the denominator squared. I didn't even talk about that. Let me go back up here. Right here, limit as h approaches 0 of g of x, that will just be g of x, right? Look at this one. Limit as h approaches 0 of g of x plus h. Well, as h approaches 0, g of x plus h will just approach g of x. So limit as h approaches 0 of g of x, that equals g of x. Limit as h approaches 0 of g of x plus 0, that just equals g of x. G of x times g of x is g of x squared. And here you have your next derivative rule. It's called the quotient rule. So let's go back up. This question, if this was your function, how would you find the derivative? Well, let's do it together. You ready? The derivative with respect to x of y, where y is function divided by a function, is derivative of the numerator times the denominator untouched, or 6x plus 2 times x squared minus 16, minus the numerator untouched times the derivative of the denominator, which is 2x, all divided by the denominator squared. Okay? And as you know, I am not concerned with you multiplying these out, combining like terms, all that stuff. If you need the algebra practice, then you go ahead and please do that. Okay? You just added to your arsenal. Okay, now we're going to take a big, big step. We're going to enter the world of trigonometric functions. And the question here is, if, let me squeeze it in here, if y equals sine x, comma, what does dy dx equal? And I'm going to pause for a second and say, does y equal sine x allow me to use the power rule? No. Is sine x a constant, in which case dy dx would equal 0? No. Is there a product of functions going on here? No. Quotient? No. All right. So what do we do? All right, so before we launch into this proof, and again, this is when we're going to just talk through and read from your textbook, there are two prereqs for this proof. The first one is old news. You've seen these before. One of them is this one. You know, if you look at this limit here, as h approaches 0, sine h over h. Oh, what does that approach? It equals 1, because as h approaches 0, the argument of sine approaches 0, and you're dividing by that same argument of sine. We know that. You also need this prereq. the limit as h approaches 0 of 1 minus cos h over h equals 0. Well, in this class, boys and girls, we don't ever take anything for granted. We're going to say, wait, we never memorized that. Why is that? Well, let's go over here and figure out why. Let's see. Here is the limit as h approaches 0 of 1 minus cos h over h. It equals 0 over 0. Oh, indeterminate. Need to investigate further. We can't assume anything of this limiting form. And here, just follow the gray here. Ignore the red for now. Well, I'm going to do this. I'm going to multiply the numerator and denominator by the conjugate of the numerator. Why? Because, look at the next line. 1 minus cos h times 1 plus cos h becomes 1 minus cos squared h. H times the quantity 1 plus cos h, I'm just going to leave it as h times 1 plus cos h for now. I love this. Why do I love it? Because 1 minus cos squared equals sine squared. Now look at this. As h approaches 0, one of these sine h's over the h will approach 1. But that leaves me with 1 sine h left in the numerator and 1 plus cos h in the denominator. So the point is, let's take a look. Indeterminate form, messed with it, cleaned house, and now once I've cleaned, I'm going to take the limit again and see if I have any progress. Well, as h approaches 0, sine h approaches 0, 1 plus cos h approaches 2, not 1. Whatever. It's embarrassing. It should be 2. Because cos of 0 is 1. 1 plus 1 is 2, and 0 over 2 equals 0. Okay, so now that I have, as someone who's a very intelligent, active reader, you know, the text says we have to remember these, and I'm saying, well, that I know. Where'd that come from? You'd go over there and try and figure it out. Okay, here we go. Ready? Well, let's use the definition of the derivative to find dy dx. So we're going to look right here. See how sine of x plus h is just f of x plus h minus f of x over h. Okay? Because here I could have called this y equals sine x, or I could have called this f of x equals sine x, right? All right. So here is f of x plus h minus f of x all over h. Oh my, but remember, sine of a plus b, remember this? Sine of a plus b equals sine a cos b plus sine b cos a. So that's what's done here. Sine of x plus h just equals sine x cos h plus cos x sine h minus sine x. So great, I love that. And then sometimes when you're reading derivations, they kind of make these great leaps and you may not be able to follow them exactly, so that's why I'm here to help you. What I'm going to do here is from this step to this step, I said, do you see where this came from? And then I kind of walked you back over here. All that happened here was, okay, that was the line prior, and the position of this term and this term were just swapped. So now they're here and here, okay? And then in the first two terms, sine x, they took these two terms all over h, plus then this last term all over h. So basically they took a single fraction and split the fraction, same denominator, so all good. And then here, sine x was factored out, right? Sine x is factored out, and if you factor sine x out, you will have sine x times cos h minus 1 all over h plus cos x sine h all over h, which is this line right here. Okay? I think the only difference here is that, see how I wrote it this way? This is, again, algebra and arithmetic, everyone. This is the same thing as just sine x times cos of h minus 1 all over h, because multiplying fractions, you don't need a common denominator, you just multiply across, okay? So that brings us to this line right here. Everyone good? Okay, very good. Well, we know that, and then it looks like, okay, so then it looks like they moved this term to here, and factored a -1 out of the numerator and a -1 out of the denominator. Factored -1 out of the numerator to get a negative here, okay? And they moved this term over here. Okay, it says algebraic reorganization, also some arithmetic reorganization. Okay, then we're looking, let's see, then again the limit of a difference is just a difference of limits, and then a limit of a product is a product of limits. So just like the proof prior, this limit applied to the entire argument. What's happened here is just the limit was applied to each component piece. You see that? Okay. And then as h approaches 0, oh my, you know this equals 1, and you know this will equal 0. That's our prereq. And at the end of the day, we get limit as h approaches 0 of cos x times 1 minus limit as h approaches 0 of sin x times 0. Well, anything times 0 just equals 0, and the limit as h approaches 0 of cos x is just cos x. Wait, this is a first for us. This is a first for us. Do you mean to say that the derivative with respect to x of sin x equals cosine x? And why is this different than the other derivative rules we've derived so far? Yes, unlike the other derivative rules, the derivative of sin x equaling cos x, we see here an actual explicit function as the derivative of sin x. Let me say that better. Whereas the previous derivative rules tended to be patterns, so to speak, okay, right? This derivative rule, like if you look over here, right? This derivative rule, like if you look at this derivative rule, it just kind of tells you what to do to f and g, right? The component pieces of the larger function to get the derivative, whereas here, this is totally crazy. What we're saying is, if I want the slope of the line tangent to sin x at, say, I don't know, pi over 6 radians, that just equals cosine of pi over 6? The answer is yes. And I even wrote, how cool is that, right? So right now, you have another derivative rule, okay? The other thing that I should say to you here is this. I went down here in purple, and I kind of organized our derivative rules. But look at my notation. Not only is it more succinct to organize your derivative rules this way, right? Because it avoids you having to write something like this. Like, if f of x equals k, then f prime of x equals 0. Here you have the statement just in one line, right? The derivative with respect to x of some constant is 0. And here's the power rule, okay? Here's the product rule. Here's my quotient rule. And here is the derivative rule that we just derived, okay? And I will say this. Once we derived the derivative rule of sin x, there is a time and place, boys and girls, to see a derivation. But after you've seen a derivation for sin x, I could certainly do a derivation for cos x and tan x with you. The derivation or the proof for the derivative of the cosine x function almost looks identical in presentation to the derivative that we just walked through. If you would like the additional challenge, or just if you're curious, if you're looking at the derivative with respect to x of tan x, I could have you derive this by expressing tan x as a quotient of sin x over cos x, okay? And then treat the quotient rule here and see if you can get the derivative of tangent x being secant squared x. So in other words, here I gave you the derivative rule for cosine and tangent just because I'm giving them to you, but you also know that where these two come from, they come from proofs very, very similar, very identical to the proof we just walked through. So, there is a point where it can be redundant to read through proofs, especially now that you kind of have the gist of what the proof would be. All right? Now, let's talk about something like this. Okay, find the equation of, all right, here you go. Find the equation of the line tangent to this function at x equals pi over 4. all right? As you can see here, we have a product of functions. So we have a product rule, but I also have one of those functions being trigonometric, cosine x. So I'm going to have used the product rule in conjunction with a new derivative rule. Go ahead and work on it on your own, and we will meet at the tail end. Okay, so if you look how I worked with the problem here, the first thing I made note of is finding the point of tangency. The point of tangency is pi over 4, comma, f of pi over 4. And look how I didn't break a sweat or create more work than I had to for myself. I just simplified where it was reasonable and left it alone. So this is the point of tangency. F prime of x, here's the product rule, derivative of 3x cubed times cos x untouched, plus 3x cubed times the derivative of cos x, and then I simplified. And then I'm making the distinction between f prime of x, the derivative function, and f prime of pi over 4, which is the derivative function evaluated when x equals pi over 4. And look what I did here. Again, nothing crazy. This is just me plugging it in, and this is me doing reasonable simplification. I'm not going to go any further. I know some of you are saying, but it's a common denominator. I'm not going to find it. Nope, no need. That's it. This number here is my slope. And then here is the tangent line, the equation of the tangent line. Y minus y1 equals m times x minus x1, where x1 and y1 are a point of tangency. Okay? Okay, so I guess the point that I have for you is, you know, as we are kind of paving our way and moving forward, we are generating derivative rules, right? And we are starting to see how all these derivative rules can be applied. And we've done our first major application in the way of tangent line problems. Now your homework from this screencast, it's going to look like a lot, but in fact, much of this is just kind of algorithmic. What does algorithmic mean? You're just working through step by step of a procedure. It's not hard math-wise. It's not really even hard high-level thinking. It's just working through the procedure of taking derivatives. Okay, here is the homework for tomorrow. Again, it looks like a lot, but it's not. None of these questions are hard in the kind of thinking hard, like, you know, thinking really deeply. They're mostly just kind of robotic working through derivative rules so it can become really smooth and, you know, just smooth and seamless with that very foundational part of calculus. Okay? All right, I'll see you Tuesday. Goodbye.